Well, welcome back to the podcast. My special guest today is Dr. Stephen Potts, who is the Chief Scientist for the Human Research Program out at Johnson Space Center. Steve, good to have you on.
Hey, thanks, Richard. Great to be here.
Absolutely. So I reached out after reading a little bit of a post that was on JSC's Facebook page about research that you guys are doing to get ready to ultimately try to get humankind to Mars. So let's see if we can. I know that it's a nebulous subject, but let's take a couple of things in there. If you can, give it a basic overview of what's going on at JSC and your involvement in that program.
Sure. I'm with the Human Research Program, and what we do is we look at how spaceflight affects the human body, and we split that out into a number of risks to the human, right, for space exploration. We have about 30 of those risks that we've identified. And we do research. We sponsor research at many universities and businesses around the country to look at those risks so that we can find mitigations. And we call those countermeasures, right? Because we're NASA, everything has to be a little different. If you go into your doctor at the clinic, they just call penicillin a treatment. We call that a countermeasure. But that's just the way we phrase things here. But so we're looking to mitigate any of those detrimental effects that may happen from going into space. So we look at behavior, we look at all the different systems of the body, anything you can think of under the human health and performance kind of genre is what we're doing.
Okay. I know in some of the previous stories I've done with, I've done some stuff with different research that is kind of tied into this. And I know a lot of stuff that's been learned on the ISS is, lack of gravity affects things of the body, like maybe even blood flow, and even it can affect the eyes and stuff like that. So talk about maybe 3 or 4 things that the human body does not like about the zero gravity environments.
Yeah, we're born here on Earth and we're used to that 1G, if you will. And when we go into microgravity, one of the main things that happens is there's about 1 liter to 1.5 liters of fluid that's just kind of hanging out in your gut and your lower body when we're here on Earth. Gravity's pulling that fluid down. But when you go into space and you experience microgravity, all of that fluid moves up towards your head. We call that a cephalid fluid shift. And that fluid does a lot of different things, right? Your body can sense it, it can detect it, and it thinks you're experiencing high blood pressure because it's stretching out your blood vessels. And so it responds to that. And part of that response is for you to lose fluid, right? Because it thinks you have too much. And so if you come back to Earth after that happens, now you don't have enough fluid. And so you can end up with low blood pressure. We call that orthostatic hypotension. And that's something that we did a lot of research on in the past. And we have a really good way to mitigate that now. But that fluid shift also affects other things. It affects your sense of smell and taste. And it's also thought to contribute to a syndrome that we call SANS. So that's spaceflight associated neuroocular syndrome. And you mentioned the change in the eyeball, right? So that is also thought to be affected by that fluid shift. And that's one of the most important risks that we're looking at for going to Mars.
Okay. Now, we're talking about fluid shifting around in the gut and then hypertension and then also in the eye. Now, in the eye, is that affecting the vitreous fluid?
So it's doing a couple different things, right? So the idea, and again, this is research, so this is a hypothesis. We don't know if this is exactly what's happening, but when the fluid moves up, it can affect the pressure inside your skull and inside your eye. And so those pressures can exert, a tension on the eye. And so one of the things we know that happens is we call it globe flattening. So your eye shape changes. So the back of your eye gets flat, and that can change the way your eye works. It can change your vision. We also know that the back of the eye, or the retina, can also get these wrinkles that are called folds, choroidal folds and retinal folds. And those are things that we're looking at as well. There are other parts of this syndrome, and there's some question about whether or not the brain is involved as well. So a lot of the research we're doing now is looking at any small changes that may occur in the brain that are related to this syndrome.
Okay. Now, I know 240, 250 miles above us at any given time would be the ISS, and I know that's our portable space lab, and there's a lot of research that's done. A lot of the research that we're alluding to here about the eyes and everything else is based on research at the ISS. And it seems to be a really good lab for those purposes. But going from there to the moon, I would affect it. I would imagine that going even further out like that would have more effects on the body. I know there's not a lot of humans haven't had a prolonged presence in the moon. I mean, they were there for a short amount of time back in the 60s when they landed, but certainly don't know what it would be like, a month on the moon. And I know anything would be speculation, but based on the research you have, how do you envision, or how does your research envision the effect that might have being on the moon for maybe a moon? Would it exacerbate what people are experiencing on the ISS?
Yeah, it's a really good question, and you alluded to the answer is we don't know, right? So
Right.
We're familiar with 1G here on Earth, and we're fairly familiar with up to 6 months of what we call microgravity on the space station. Now, the moon has a partial gravity environment, so that's about 1/6G. And the question we all discuss is, what is 1/6G, right? Is it closer to microgravity or is it closer to 1G? And if you're thinking very linearly, you'd say, well, it's closer to microgravity or close to 0G. But really, we don't know what the shape of that curve looks like. And that's the important part. So we're doing a number of different things. When we do our research, we sort of have this three-tiered approach, three-phase approach, or you could even call it a stepped approach, right? So we do a lot of research here on Earth. We try and replicate as much as we can about microgravity and other aspects of the spaceflight environment. So we study a lot here on Earth in what we call analogs, whether that's bed rest or isolation facilities or things like that. And then, well, like we discussed, we do a lot of work on the International Space Station. We have dozens of experiments at any given time on the ISS looking at the microgravity component. But we're going to do the same thing when we go to the moon. We're going to use the moon as an analog for Mars, right? Because the moon is a partial gravity environment. Mars is a partial gravity environment. So the first time we're really going to get to study this partial gravity environment for any, significant duration of time will be once we land on the moon. So we have a number of studies that we're looking at to make that transition to go from one place to another so that we can then extend it. So we're looking at the Earth for low Earth orbit. We're looking at low Earth orbit for the moon and Mars, and then we're looking for the moon to help us get to Mars.
So we were speaking about some of those analogs. I know you have like CHAPEA, and there's other stuff out there that people are in. And in fact, I think I just saw where the current crew in one of those analogs is about halfway through their mission, if I'm not mistaken, or roughly halfway through. They gave a Christmas update, and wishing everyone Merry Christmas. What has been some of the research that's come out of that you can disclose? I know there's probably still a lot that's being processed and learned about, but so far, what's some of the stuff that's come out there that you can talk about that you think is going to help in getting us further and further out in the solar system?
Well, none of the data has been analyzed yet, right? That won't happen until CHAPEA is over. So I can't really tell you any data from that, but I can tell you one of the primary things that's being